Okay, so I want to talk briefly about the total ring of fractions of a reduced ring. So total ring of fractions. Okay, so this is like the generalization of the fraction field of of a domain. Okay, so the field of fractions of a domain. And so our kind of goal with this, so kind of one of the goals, is to show two things. Is to show that OL, so that OL is the integral closure of kappa of t in T, where here T is OK1 tensor. So we had like a tensor product of fields here, and so kappa of T is the field of fractions of T. Okay, I'm going to say field of fractions, but it's the total ring of fractions of T. Okay, so so it's not field, so it's the ring of fractions. It's not going to be field. And then the other thing that I want to show is to show that kappa of T in this in a particular case, this tensor product of fields, this is equal to a direct sum of fields. Okay, so for each embedding. Okay, so this is actually this is not what I want to show. That's true, but that's after a Chinese remainder theorem. I want to show that it's just this tensor product of fields. So like you can take the field of fractions of this arbitrary this abstract tensor ring, and then it'll be this this tensor product of fields. Okay, so these are not really necessary for doing things, but I guess it just kind of cleans things up nicely. And so okay, and so what do I mean by OL here? Of course, so OL in this case, so we are going to take K1 through Km. It is going to break up into a tensor product, okay, over a certain index. So these run over tuples of embeddings, and then we can say OL. We can define it to be the field of fractions, or sorry, we can define it to be OL psi. So for products of fields, we can define it this way, and then it'll turn out that these will be all the integral elements. Okay, so that's what I want to say. These are the goals. All right, so let's start with the lemma about the total ring of fractions. So lemma. So let R be let S be a subset of a ring R, be a multiplicatively closed set. Okay, and then we just want to remind everybody that this is LS from R to S inverse of R is not injective. If and only if S contains a zero divisor. Okay, so let's do the proof of this. This is not bad. So the forward direction, so if we have something in this localization map being 0, so this is the same thing as being this equivalent to 0, which is the same thing as saying that there exists some S and S such that SR is equal to 0. So therefore S contains a zero divisor. Okay, conversely, right, if S and S is such that RS is equal to 0, right, then R over 1 is equal to 0 as an element of S inverse R. So this localization. So this is by the same reasoning. Okay, so all right, that's all I wanted to say about that. So yeah. So if you know, so this is it, and so the point is that if ls of a is equal to 0 for some a, then a is a zero divisor for s for the multiplicably closed set. All right. Okay, so now we can go and go ahead and define the total ring of fractions. Okay, so total of fractions. So we want to take the maximal localization. All right. So so definition. So let R be a reduced ring, or I guess R be any ring. I guess. Okay. So so kappa of R is the total ring of fractions of R. Of R, and so this is defined to be S inverse of R, where S is the set of non-zero divisors. Okay, so that's what the total ring of fractions is. Most basic example. So if A and B are domains, then S looks like SA cross SB. So this is the set of AB where A is not equal to 0 or B is not equal to 0. Okay, then in this case, so these are the set of non-zero divisors. So in order to have a zero divisor, one of the components must be 0. So then S localized at A cross B, well, this is S localized at A, SA localized at A cross SB localized at B, or localization of B at SB, and so this is just the field of fractions of A cross the field of fractions of B. Okay, so that's what we have going on. Okay. All right. Okay, so let's do a definition. Okay, so okay. There's kind of an exercise. I actually need a lemma here. So lemma. So so let's do an exercise. This has to do with prime avoidance. Okay, so it says that if R is a reduced ring, then the zero divisors of A so the zero divisors of R, so it's the union of P, where P is a minimal prime ideal here. So this is the set of minimal prime ideals. All right. Okay, and so the idea, the trick here, the key trick here is that you can use prime avoidance. So the proof I know uses prime avoidance. Okay. All right. So Okay, so now let's do the following. So here's a following proof. So okay, here's a lemma. Okay, so if A is a reduced ring, then the map A goes to its field of fractions, or its total ring of fractions, is injective. Okay, so here's the proof. So this is just another incarnation of the thing that we said about localizations in zero divisors. So a localization LS is injective if and only if S contains zero divisors. And by definition, right, this is, S max is the, S is equal to S max is this collection of non-zero divisors. So the map is injective. So this is just like repeating what I said before, essentially. And actually, I guess this is actually for any ring. It doesn't necessarily need to be reduced. You just take non-zero divisors. Okay, so all right. Now I'm gonna continue with the structure theorem for this the total ring of fractions. So the theorem is the following. So it says that so it says that here says that so if A is reduced, then cap of A looks like the direct sum for P minimal prime ideals of kappa of P. Okay, so this is the structure theorem. So the idea here, the idea is like if you have a bunch of different components, right? So if this is spec A, right, and you have a bunch of different components, then the total field of functions, total ring of fractions, is equal to the direct sum of the function fields of the irreducible components. Okay, so that's what this says geometrically. Okay, so let's do a proof of this. Okay, so if A is reduced, then the zero divisors so these are the unions from, so let's say that it's like Noetherian, so we have a finiteness, so we have finitely many minimal prime ideals here. Okay, so the zero divisors are the union of the minimal primes, so minimal. Okay, so so now we're going to let K be this product of these. So let K be the direct sum of P in the minimal primes. And then we're going to do kappa of P. Okay? So if S in A is a non-zero divisor, then the localization map here, this is not equal to 0, and LPS mod, so this thing modulo the maximal ideal at P is not equal to 0. So there's a maximal ideal corresponding to each one of the components. Okay? So, great. So, okay, so if you have a non-zero divisor, then when you localize at the prime ideal, which is the complement of, the complement of the, so you're localizing at the set, which is the complement of the prime, then it's not going to be 0. Okay? So, all right. Okay, and so that's just because S is not a zero divisor. Okay, so what does this imply? So this implies the image of S under L. L, this is like the big localization, is invertible. Oh, that's actually not L. So the image of S under L. So L, the L is from A to K here. This is the direct sum of the kappa p's, is invertible. Okay, so here A maps to K, and S maps to, well, LP1 of S mod MP1 LPR of S mod MPR. Right? So we have this map here. This is the map L. Okay? So the image is invertible. Okay? And so okay, so by the universal property of localization, so we have the following. We have this factorization like so. U, okay? So this is, we'll just call this L max, like so. This is our map L. So this is because, this is because the image of S max under L is invertible. Okay, so okay, also also U is an injection for the same reason. Okay. So it remains to show the map is surjective. Okay, that is so for all xi in kappa pi. So there exists some x in S max inverse of A such that x mod MPI is congruent to xi bar. Okay, so so now we're going to use a little property about localization. From the description of localizations, of spec of S inverse of A, so we have the following. We have that spec of S max inverse of A. Okay, this is the set of P in spec A such that P intersect S max is empty. Okay, so we get rid of prime ideals if they intersect what we're localizing at. So if P is not minimal, then this thing here is not empty, since it contains something in the complement of the union of minimals. Okay, so hence the only primes that remain the only primes that are remaining under the correspondence are the minimal ones. So this implies the only primes remaining under the correspondence are the minimal ones. Okay, so that is what I mean to say is that spec x max inverse of A. So this is isomorphic to the set of S max inverse of P for P in the minimal prime ideals of A. Okay, that's what we have. Okay. Okay, also, as each of these primes as let's say these are the only primes, they're maximal. Okay? Okay, and so since localization commutes with quotients, we have we have that S maximum inverse A mod P is isomorphic to S max inverse A modulo S max inverse P. Okay? So it remains to show S max inverse of A mod P is the fraction field of A mod P. Okay? So, okay, so since it's reduced here, right? So So reduced, right? We can conclude that S max inverse of A is, well, so this is equal to the intersection of S max inverse P, so these are the prime ideals, Pi, okay? And then this is by the Chinese remainder theorem. So they're maximal, so then they're piecewise or pairwise, they are the biggest things. Okay? So this is what we get. Okay. So, okay. Okay. So, okay, so what do we have left to do? So it remains to show that this quotient here is as advertised. Okay, so so here's an indirect proof of this. So here's the proof of the last claim. So note that we have the following. So we have A, right? We can localize it, and then we can take a quotient. Okay, we can consider the composition of these things and call that phi. Okay, so this is what we'll consider. Okay, and so since we have that S max inverse, so this behaves well under quotients, right? So this is isomorphic to this. So we have the following. We have another factorization, and the other factorization is as follows. So it's that A goes to A mod P, right, goes to this thing, which goes to A mod P. Okay, so so this is what we mean by, okay, so we'll call this thing L max, L S max. Oh, sorry, it's not the one I want to do. So I want to do the localization from here to here, right? This is LS max. So S max is the image here. The bar denotes the image in the quotient of the multiplicably closed set. Okay, so since S max inverse has no zero divisors, it has no kernel. This map here has no kernel modulo P. And hence, the kernel of phi is this. It's just P. The kernel of this whole thing is this because of this other factorization. Okay, so also, since this other thing is a localization with respect to a multiplicably closed set, closed subset of A mod P, okay, which is so since it's a localization with respect to a multiplically closed subset of A mod P, and the image is a field, it must be the field of fractions. Okay. Okay, so I want to give a characterization of the total ring of fractions. So characterization. Okay, so here's the lemma, or theorem. So let R be a reduced ring. Okay, and so let S subset of R be multiplicatively closed. Okay, so if 1, this map here is injective, and 2, that this is a product of fields, okay, then then S inverse of R is the total ring of fractions of R. Okay, that's the characterization. Okay, so proof. First, so actually, let's not do numbers. So, if R maps to S inverse R is injective, it contains no zero divisors. So S contains no zero divisors. And hence, S is contained in this maximal one. Okay? Okay, so this means that, so this implies that we have a factorization as follows. Right, so we can localize, and then we can localize again. Like so. Okay? So we have a map from here to here, and it's injective. So conversely, if R is not a zero divisor, then neither is LS of R. So by the characterization of the, so now by the characterization of zero divisors of fields, of of products of fields, LS of R, so let's say the image of R in each factor, so let's say the image of LS of R in each factor is non-zero. Okay? So this implies, right? So this implies that this thing here is contained in S inverse of R cross. So this shows every non-zero divisor of R is invertible in S inverse of R. Hence, we get a factorization the other way. Right? So this means that S max is contained in S, and S is contained in S max. So we actually have this. So for saturated, so for where the bars denote saturations, right? So here you join all the units to your multiplicatively closed set. Okay, so so this proves the result, all right? Okay, so here's a question: is so here's the question: is OK1 OKM reduced? Does it have nilpotent elements? Right. So so let me just say so let me just show that in general the tensor product of reduced rings is not reduced, right? Of reduced rings is not always reduced. Okay, and so the example here is to consider something like z adjoin the square root of p, tensor it over z with fp. Okay, and this thing's isomorphic to fp adjoin x modulo x squared. Okay, and then this is not reduced because x, the class of x squared, will be 0. Okay, so so this is something that we can worry about. Okay, so and we worry about this because we want to talk about the total ring of fractions of this tensor packet, right? This tensor product. Okay, so so the claim here, so the lemma that I want to prove is that so the claim is that this tensor product here, the tensor products over, say, if these are p-adic integers, then, or sorry, p-adic rings, and these are rings over the p-adic integers, so this is reduced. Okay, so this is what I want to prove, and so how to prove this, right? Okay, so how do we see that the map is injective? So see that this map OK1 OKM into K1 KM is injective. Like, if we can show that this is injective, then this doesn't have any nilpotent elements, so this won't have any nilpotent elements, right? And maybe it's not the case that this is injective, right? It is, right? And let me show you how that works, right? So the thing is to not think about it tensor-wise, but use another presentation, right? So the wrong way, so here's the wrong way to do it. So you look at this map where you take sums of AI's tensor BI's over ZP, and then you map it to a sum of AI's tensor BI's over QP, right? So this is this is confusing. Okay? Okay, so the right way of doing this, or the easy way, right, is to write each element here as a primitive extension. So where Fi is irreducible and monic. And okay, and so this thing exists, okay, for p-adic fields. Okay, then we'll have that OK1, OKM. Well, this looks like a product of, so it looks like a tuple like this, and then we're modding out by these polynomials here. Okay, and similarly, K1 to Km is also a product, or is also a polynomial ring like this, right? And so this allows us to see this easily, right? So this to see that if this is T and this is V, that allows us to see that T includes into V, among other things, like as well as things like OKI includes into T and KI includes into V. Okay, and so so as a corollary of the injectivity is that this tensor product is reduced. Okay, and so yeah, so that's something nice. And so the kind of upshot, well, is that we don't have to worry about things with this integral closure. Okay, so all right. I mean, yeah, we can include something, we can inject it into its ring of fractions. That's what I mean to say. Okay, so we're going to use this characterization of the total ring of fractions. Okay, so the first step is we'll use commutation with tensor products. So here we'll use that SP inverse tensor I is equal to 1 up to m of OKI. So this is equal to QP tensor I is equal to 1 up to m of OKI. And this distributes tensor QP. Okay, so this is just the product for I is equal to 1 up to m of KI's. Okay, so these guys are like this, and so this is and then this side is this. So here so SP is 1 p squared, etc. Okay, the second property we need to check. All right. So, right, the second property we need to check is that here, so we'll have this map here. We need to check that this thing here is injective. Okay, and so this is easily seen by looking at the polynomial algebra. So this looks like ZP x1 through xm, adjoin some polynomials and mod them out. And then this is exact same relation, so you get no new relations here. Okay, so so the map is injective. Okay, so there's no zero divisors. Okay, and so the third thing is that it's a product of fields. So the last thing we need to check is that by the Chinese remainder theorem, this thing here, I is equal to 1 up to m of fi, is a product of fields. So we're done. And we've shown that this thing is the ring of fractions. Sorry, the total ring of fractions of this is the tensor product of the fields.